Hello students, welcome to the session of Metrology and Quality Control. In today's session we'll discuss about metrology. So metrology is nothing but a Greek word used for measurement, that is metro means measurement and logy means a science, that is metrology is the science of precision measurement, we call it precision. So before that, measurement is nothing but a process of numerical evaluation of dimensions or process of comparison with the standard measuring instruments. So what are the standard? We'll discuss it in further slides. Again, measuring system include instrumentation, calibration standard, environmental influences, and with the workpieces and human operators. So what are standards? Standards of measurement is nothing but usually the universally accepted processes or devices. So for that purpose, some of the components or processes which are to be ensured for conformability and interchangeability throughout a particular industry, or we can say that worldwide. So first type of standard is nothing but a calibration standard. It is nothing but a working standard of industry or a government laboratory. Or next one, methodological standard will be nothing but a reference standard, and third one is the national standard, which is nothing but a prototype accepted universally or worldwide. Further, linear measurement, that is based on either line standard, inch standard, or wavelength standard. So we'll discuss these three standards one by one. Line standard is nothing but the distance measured between the two parallel lines, that is with the help of a steel rule. So distance measured between the two lines, which means we have to draw two lines with the help of a steel rule, and so 2 point distance we can say that is nothing but a line standard. Usually it is a direct length comparison method which requires no auxiliary devices. So with a single instrument, example was steel rule, can be used for line standard. So yard meter is one of the line standard. Next one is the yield standard. Yield standard is nothing but the distance measured between the two surfaces. Now two surfaces usually will be, or maybe two blocks we can use, or two flat surfaces for measurement. So compared with the line standard, it provides the accurate and very small dimensions can be picked up or measured with the help of the yield standards. So usually that may be length bars, sine bars, etc. So compare between two standards. So as the high accuracy is there for yield standard, so manufacturing cost will be higher, time required for measurement will be higher, then errors may be improper ringing we'll discuss in further sessions, but parallax error may be the important error which may occur in our line standard. So important applications may be, or examples may be length or slip gauges and meter and yard. And third type of standard is wavelength standard. Wavelength standard compared with line and yield standard is the accurate standard because physical components, instead a light source which is nothing but a monochromatic light source which is natural and static is used for the wavelength type of a standard, which reduces the dependency problems of physical standards, which has no effect of variation in temperature, pressure, or other environmental effects which may be present in the line measurement or yield measurement. So monochromatic light source may be of a krypton 86. So this standard relation is to be remembered, that is 1 meter is equal to 1650763.73 into wavelength of radiation. Next one is calibration. So calibration term means bringing a measuring system in accordance with the external authority, that is the standards using. So for example, if you consider calibration, or if you have to calibrate a balance which means for that process we should know masses which are having the known values, that is standards we can say, and then relate these responses. Suppose this is a balance, its value, and 1 kg of mass is kept over here. This reading should be 1 kg. If not, we have to calibrate this instrument. So obviously we have to do this in a lab. Next process is nothing but traceability, or we can say the term traceability. It is nothing but chain of calibration processes. So number of steps are followed from higher institute in the sense standard maintenance, so national standard, workshop standard, or universally accepted standard. So from that process we have to accept, that means primary standard we can say, then we have national standards. So standard which is universally accepted worldwide, there is, suppose a prototype is to be prepared of platinum iridium bar. So from that process we have to again measure the values with this, that is K20 model, then that is to be transferred. So this process is nothing but tracing the values, so we call it as traceability. So lastly, in our laboratory we have working standards. So for getting traceability we should have a certificate of accuracy, such type of accuracy certificate with some values provided by national institutes, that is Institute of Standards and Technology. So we call the value as traceability. Next part is error. So what is error? Is nothing but the difference between the true and actual value, or the difference between the measured value or true value. So errors are divided into three types: gross error, random error, and systematic error. So gross error, that is blunder. Blunder in the sense we can say number of factors affecting for getting the error. So number of readings if we take for any of the instruments, then also we'll have a number of errors in that. So usually error is defined as quantity which is equal to difference between true value and the indicated value when the measurement process is done. So first type of error in that is systematic error. Systematic error, also called as controllable error. So this error includes calibration error, or during here error due to the variation in atmospheric conditions. Next we have random error, which doesn't have any cause, that is randomly occurs during our measurement process. So this may be due to displacement of level joints of instrument or backlash, friction. So generally it is introduced due to friction. Next one we have environmental error due to environmental factors like nuclear radiation. Alignment error, cosine error is shown over here. Suppose you have to measure the length L, but we will measure this L due to the improper alignment. So we can say that this theta angle will be introduced, which we will call it as a cosine error. Same case or same example is shown over here. So instead of placing the dial gauge over here, it is placed at an angle due to the surface grid. There may be number of reasons or maybe causes, and this theta introduces the error. That is, if you consider it as a triangle, so based on the cos theta process we will get the error over here. So it is also called as a cosine error. Again, next type of error which may occur is elastic deformation, or due to elastic support. So this may swag or hag. So this contact or this pivoted points may provide the errors, which we call it as a support error. Next, dirt particles due to environmental effects. Next one we have contact error, that is, if we see this diagram, if you have to measure the thickness over here for a curved part, so this gap will be major or additive part in the value. So this we call it as a contact error. So for this, different contact points are to be used. Next we have parallax error. Parallax error, we can say that the observational error. That means one observer may say that the reading is this one which is shown over here, or other observer will show that this is the reading, but actual perfect reading should be observed. So we can say that parallax error can be eliminated by observing perpendicular to the values. Next one we have errors lead to the uncertainty in the measurement. So that means we never expect, or we can never know the exact or true value for any of the instrument. Some sort of errors may be there. So idea for a true value is abstract, which is never knowable. So in practice, we are too close, or we should be too close to our actual values. So uncertainty is nothing but estimate of inaccuracy of a measurement that includes both random and systematic error. Again, it is also an instrument of range within which the true value, suppose this is our one value which is nearer close, and between this we will get our all the values. So it is nothing but a probability. Uncertainty is nothing but a probability. So it is very difficult to state with certainty how much uncertainty there is in the measurement values, but obviously metrologists will continue to the process. So methods of measurement, first one is direct measurement, in which direct contacts will be there with the instrument, that is scales, calipers, micrometers, contact type, non-contact type. Second, we have indirect measurement, in which one value is to be measured and then it will be converted into some values. Third one, we have absolute values, that is measuring the fundamental values. Next one, we have comparison, so get one value, compare it with other values, so it will be done with the help of number of comparators, and likewise we have different methodologies. So important again is measuring instruments and their classification with selection. So measuring instruments are classified based on first one, function. So for what type of measurement it will be used, that is if length measuring instrument, angle measuring instrument, surface measuring instrument, likewise. Next one, we have accuracy. Based on accuracy we classify the instruments as most accurate, moderate and below accurate. Again, on the basis of precision, we classify instruments as precision measuring instruments and non-precision measuring instruments. Next is factor affecting accuracy of measuring instruments. So what are the different factors which will affect the accuracy? So first one, we can say that calibration factor, that is standard of calibration for setting accuracy. Next one, we have workpiece control during measurement. Then inherent characteristics or human factor may be there, so improper calibration or either the environmental conditions. Next, we should remember the 7 basic units, that is length, mass, time, electric current, temperature, luminance, intensity and amount of substance with their units. And some supplementary units with that, we should also know the derived unit. So various precision measuring instruments are nothing but slip gauges, screw thread and depth measurement instrument, that is micrometers, vernier calipers and vernier height gauge, which has the ability of accuracy up to plus or minus 0.02 mm. So this is the first instrument, we call it as a vernier caliper. Again, we'll discuss all these instruments in our upcoming sessions in detail. Time being, in today's session, we'll continue with just the pictorial views and the introductory part. So vernier caliper used for linear measurement, which consists of inner jaws and outer jaws. So it will provide us the values with some sort of least count of 0.02 mm. This detail again will continue in our further sessions, how to calculate least count, but important is to be understanding the least count. Least count is nothing but, if question is asked define least count, so least count is nothing but the smallest division which is provided on the any scale. So if we consider a general steel rule, so what will be the smallest value over here? That will be nothing but 0.5. So similar case, now we have for vernier caliper least count as 0.02. So how it is? It is nothing but smallest division on main scale. This is the main scale divided by number of divisions on the vernier scale. So if number of divisions on vernier scales are 50, so 1 divided by 50 is nothing but 0.02 value. Similar fashion, we have other instruments and for which least count can be calculated. And how to take the reading? For that we have to go for main scale reading with the vernier scale divisions, which will coincide with the, suppose this value is coinciding over here, so 8 into least count plus mean scale reading. Another instrument is vernier height gauge, which will be used for measuring the height of any component. Vernier depth gauge, which will be used for depth of measuring instruments. Another important instrument is micrometer, which is shown over here, which consists of important part as a barrel, as main scale, and a circular scale, we call it as a thimble, which usually has different ranges for the instruments. Again the same type, main scale over here, smallest division on main scale divided by total number of division on thimble, that is we call it as a circular scale. So likewise, screw thread, the ends will be varying, so we'll get the different measurement. These are the actual instruments on which we'll get the value. Next, the instrument may be derived for digitality, that means digital instruments can be used, which will provide us the direct value with some sort of circuits. Next one, we have depth micrometer, similar to depth vernier calipers. So the actual process is shown over here, that is measurement using the depth micrometer. Sleep gauges are usually nothing but the standards ringing process. Ringing is nothing but combination of two slip gauges together, so it is nothing but a stepwise process in which we have to combine without any air gap. So suppose 6 mm slip gauge is there and 2 mm slip gauge is there, so it has to be combined together. For that, longitudinal combination should be there, applying some sort of pressure, and then just rotate it in clockwise direction with a slight movement, and there will be combination. So adhesive nature will create a block by eliminating the air. Then non-precision instruments, we can say that ruler, filler gauges, gap gauges likewise are shown over here. So calipers, these are the following calipers, which are non-precise, which doesn't provide the numerical values. Filler gauges, that is to measure the gaps between the spark plug. One example shown over here, that is ignition point. So if you have to measure the gaps between any surfaces, this example is a filler gauge. Again, this is the gauges. So over here, filler gauge to measure the gap between the spark plug. This will be the usual application. Again, it is classified into, so whatever are the components over here, so the gaps between this can be measured using the filler gauge, which is shown over here. Next one, we can check the gap between the piston ring and piston. Next one is telescopic gauges. Telescopic gauges is nothing but to just set the values, and then with the help of direct instruments we can measure the values. So direct instruments may be the micrometers. So set the value over here, lock it using this, and these two values can be measured using the another instrument. We call it as a micrometer. Inside micrometers, that means to measure the inside values. For holes, we have small hole gauges shown over here. Dial indicator, dial calipers, which will be dealing with our second unit. Pressure gauges are there, vacuum gauges are there, which we see in our motors are. Then angular instruments, so likewise protectors, sign bars, sign centers, autocollimators, which will be used. So thank you for today's session. In next sessions we'll move on with our few further topics. Thank you.